Hi, welcome to Chemistry with Caroline. In this video, we're going to look at how to calculate formal charge for atoms that are important in organic chemistry. So in organic chemistry, we're really looking at molecules that are predominantly made out of carbon and will have hydrogens on them. And then we use a few other atoms that we call heteroatoms as well. So we're going to be looking predominantly at kind of this section, and we can look down a column, and things often behave the same way down a column in the periodic table. And so that allows us to pretty easily ascertain formal charge for a grouping of elements. So formal charge is sort of a bookkeeping of electrons in a molecule, where they're likely to reside. It does make some assumptions. It's not perfect, but it is really good at predicting reactivity of atoms and molecules. So the formula for formal charge is the number of valence electrons that atom has minus the combined non-bonding electrons plus 1/2 of the bonding electrons. So essentially, the non-bonding electrons are not shared. They're on that atom, and so we count the total number of non-bonding electrons. Those would be like lone pairs of electrons, or it could be an unpaired electron like in a radical. And then we make the assumption that the bonding electrons are shared evenly. We know from dipole moments that that's not true, but again, it gives us a general idea of where electron density lies in our molecule. So if we go back to our periodic table again, I'm just going to draw this part here. So carbon has 4 valence electrons, nitrogen has 5 valence electrons, oxygen and sulfur, everything in that column, have 6, and the halogens, fluorine, chlorine, bromine, iodine, have 7 valence electrons. So the number of valence electrons on an atom is given, and then we would just look at the particular atom to figure out, in that case, how many non-bonding electrons and bonding electrons it has to calculate our formal charge. So let's begin with carbon, since it's going to be in every organic molecule. Here you've got sort of 3 scenarios for the ways in which you will commonly see a carbon atom throughout organic chemistry. If we start on the left-hand side, here you have a carbon that has 3 bonds, but it doesn't have any lone pairs of electrons. So we know the valence electrons of carbon are 4. And if we subtract from that the number of non-bonding electrons, so that's 0. There's no lone pairs of electrons on carbon, plus 1/2 the number of bonding electrons. So again, we're making the assumption that each of these bonds are shared equally, so that there's essentially 1 electron assigned to each atom in a bond. So that carbon has 3 bonds, and so it would have 6 total electrons around it, 2 in each bond, and we're assigning 3 of those, 1/2 of each bond, to the carbon atom. So this would be 4 minus 3, that equals 1. Okay, so this carbon atom is positively charged because it doesn't have a full valence of electrons there. This type of carbon with a positive charge is called the carbocation, and it's a very common intermediate in organic chemistry reactions. So you'll be seeing this frequently as we move forward in organic chemistry. In the middle here, I have a couple of different examples. These carbon atoms have 4 bonds. On the top, I have 4 single bonds. On the bottom, I have a triple bond and a single bond that add up to 4. You could also have double bonds in there. Any iteration that gets you to 4 bonds. So if we did this calculation, we would have its valence 4 minus the number of non-bonding electrons, which is again 0. There are no lone pairs of electrons on either of those middle carbon atoms, plus 1/2 the number of bonding electrons. Each of these carbons has 4 bonds. Each bond has 2 electrons in it, so that's 8, right? And so that is going to be 4 minus 4, so that's 0. That type of carbon atom with 4 bonds and no lone pairs is neutral. Okay? And then lastly, we have this carbon on the right-hand side. It has a lone pair of electrons and 3 bonds. So again, the valence is 4. If we subtract the number of non-bonding electrons, which is that 1 lone pair, 2 electrons in that lone pair, so 2, plus 1/2 of the number of bonding electrons. It has 3 bonds. Each bond has 2 electrons in it. So that's 6 total bonding electrons. So that would be 4 minus 5. That equals -1. So this carbon here is negatively charged. That is called a carbanion. And carbanions are also intermediates that are found in organic chemistry reactions. So next, let's look at nitrogen. Here we have a nitrogen that has 4 bonds and no lone pairs of electrons. So the valence of nitrogen is 5. There are 0 non-bonding electrons, plus 1/2 of 8, because there are 4 single bonds on this nitrogen. And so that is 5 minus 4 equals 1. This nitrogen is positively charged. So anytime you see a nitrogen atom with 4 bonds in any iteration, those could be single, double, triple, but if it adds up to 4 and no lone pairs, it's going to be positive. You want to be able to quickly identify that. Let's look at the next nitrogen in the middle there. Again, a valence of 5. This nitrogen has 1 lone pair of electrons, so that's 2 for the non-bonding, and it has 3 bonds, so it's going to be 1/2 of 6. Each of those bonds has 2 electrons in it. So this is going to be 0, 5 minus 5. So a nitrogen atom with 3 bonds and 1 lone pair of electrons is going to be neutral. Lastly, we have the nitrogen atom on the right. Again, a valence of 5. This has 2 lone pairs of electrons, so there are 4 total non-bonding electrons, plus 1/2 of 4. There's only 2 bonds there. So this is going to be 5 minus 6 equals -1. So this nitrogen with 2 bonds and 2 lone pairs is negatively charged. And whether that was 2 single bonds or a double bond, as long as it has the 2 lone pairs of electrons, it's going to be negatively charged. Next up is oxygen. Oxygen has a valence of 6. You can see on the left-hand side, I have 2 iterations of oxygen with 3 bonds and 1 lone pair of electrons. That could be a double bond plus a single bond, or it could be 3 single bonds. The valence is 6. The number of non-bonding electrons is 2 in either case, plus 1/2 of 6, because there are 3 bonds total, and so that is going to give me plus 1. So oxygen, when it has 3 bonds and 1 lone pair of electrons, is going to be positively charged. These oxygens in the middle have 2 bonds, 2 lone pairs of electrons, so you'd have 6 minus 4 non-bonding electrons, that's 2 lone pairs, plus 1/2 of 4, because there are 2 bonds in each case. So that's 6 minus 6, that equals 0. So these atoms in these 2 central molecules are going to be neutral. And then lastly, we have an oxygen with 3 lone pairs and only 1 bond. So here, 6 minus 6, because we have 3 lone pairs of electrons, plus 1/2 of 2, there's 1 bond, equals -1. So this is negatively charged. This species is referred to as an oxide, and those are commonly found in organic chemistry as well. They're often used as bases and other reactive intermediates. And lastly, we have the halogens. So the halogens are fluorine, chlorine, bromine, and iodine. The halogens, when attached to a carbon atom, tend to be terminal. They take the place of a hydrogen atom. They would have 1 bond and 3 lone pairs of electrons. We don't typically see the halogens forming multiple bonds when attached to a carbon atom. So here we would have their valence of 7 minus 6 non-bonding electrons. They have 3 lone pairs, plus 1/2 of 2, just the 1 bond there. And that would give me 7 minus 7, which is 0. So when attached just terminally to a carbon atom on the periphery of the molecule, it's going to be neutral. The other thing you will see is halogens are commonly used as leaving groups in organic chemistry, so they will break the carbon halogen bond and take those electrons with them. So you have a valence of 7 that you would expect. In this case, you have 8 non-bonding electrons because it has 4 lone pairs of electrons. It's not attached to anything. No bonds, so you're looking at 1/2 of 0, but 7 minus 8 is equal to -1. So this is a halide. IDE tells me that it has a negative charge. So that's an overview of how to calculate formal charge for elements that are important in organic chemistry. For some context in how this fits into the broader scope of success in organic chemistry, you can watch my video, How to Be Successful in Organic Chemistry, 5 Concepts to Master, of which formal charge is one. If you found this video helpful, please like, subscribe, and share with your friends, and I'll see you next time.